Moving on to covalent compounds. Covalent compounds are two elements, nonmetals, are when they bond, they share electrons, just as a reminder. And here we have hydrogen and oxygen forming a covalent bond, right? Hydrogen by itself, and if you remember electronegativity, if hydrogen has one valence electron, and so it actually makes sense that it binds to itself and makes this diatomic molecule. Okay, because hydrogen only needs to fill up the first quantum level, and there are only two electrons here. So what it does is it forms this one single bond, uh, binding to itself and therefore stabilizing. Okay, and so this line represents two electrons, one from each hydrogen, forming a so-called sigma bond, a direct overlap of the electron in the s orbital. And it also makes sense that hydrogen would be a gas, because the difference in electronegativity between hydrogen and hydrogen is zero, right? So this is a completely non-polar bond. That means there's no electrostatic difference, there are no partial charges, and other hydrogen molecules are very unlikely to interact with each other. So they can just go about independently. Whereas the hydrogen-oxygen bond is polar, meaning the difference in electronegativity is rather large. Electronegativity of hydrogen is 2.1 and that of oxygen is 3.5, so the difference is large. Therefore, the electrons are pulled towards this oxygen here, creating a partial negative charge and a partial positive charge. It's just not equal sharing of the electron. Oxygen is more electronegative. It's going to pull that electron density towards it. And that means, and I'm going to draw the other hydrogen in, there's the same thing happening here. That means that it actually interacts with other water molecules. Okay, so there's a positive and a negative charge forming a so-called hydrogen bond. And that happens with as many water molecules as are present. And so this network increases, of course, the blob. It's not that it makes it liquid, right? It lowers the boiling point and makes it a liquid. And so you see this drastic difference here. Oxygen is the same thing. You've got an oxygen. I know some of you know that this is wrong, but for now we're sharing electrons here. So that's all that's indicating, and it's completely equal sharing. All right, it's not wrong. It's just there's just more to it than a single blob here. Anyway, and so it also is a gas, right? But when the two we have a drastic drop here or increase in boiling point here, right? So obviously there's no interaction here, and there's high, so it's an increase in intermolecular interactions, therefore an increase in melting point and an increase in boiling point. I said that wrong earlier, so it's an increase, of course, in boiling point and melting point. Very similar to when we had lithium and chlorine, we had the character, once they combine, the properties of the product are completely different than the individual elements, and the same thing is true here. Water is completely different, right? You can I didn't look at flammability, but you may have read it here, right? So you can burn up, you can blow up hydrogen, and you can use oxygen for combustion. It's going to just encourage combustibility or burning of anything. Okay, so those are covalent compounds. And here's what's happening. Here's why, right? If you had hydrogen, hydrogen has a single electron, and oxygen has 6 valence electrons. So oxygen can either gain 2 electrons from a metal and become anionic, negatively 2 charged, or it can do what it's doing here. You can have 2 of the hydrogen atoms combine with 1 oxygen in a 2-to-1 ratio to form 2 single bonds here, right? So this way, oxygen gets its 8 electrons. It's not negative, it doesn't have a negative 2 charge. It simply does this by sharing. And hydrogen also gains 1 electron, or has its full valence shell here. And so we get this water molecule as drawn here. So And that's because both of them are electropositive. They're not going to give up their electronegativity or their electron density. They are going to simply share. And you can make a lot of different kinds of compounds. Quick little summary here. We have two types of compounds, ionic and covalent. Ionic is the transfer of electrons. You have a large difference in electronegativity between the two atoms that are forming the bond here, forming cations and anions and arranging in a three-dimensional lattice as shown here. Example, sodium chloride. Nonmetals and nonmetals share electrons. The example was water or H2O. And they also arrange here in the solid in a three-dimensional, but the interactions here are different. These are hydrogen bonds in this case. All right. Okay, so how do we represent these covalent compounds or any kind of compound with a chemical formula, right? Well, every compound, every substance is going to have a certain number of atoms of each of its components, right? Like water has 2 hydrogens and 1 oxygen here. And so we write it as such. We write the hydrogen, that's the first element present in this compound, and we put a little 2 indicating that there are 2 hydrogens per water molecule, and there's 1 oxygen. And so we don't write a little 1 here, it's understood. Same with carbon dioxide. There's 1 carbon and 2 oxygens. Sodium chloride 1:1. NaCl and carbon tetrachloride. Carbon will make 4 bonds to chlorine, or will take up 4 chlorine atoms, and so we put a little 4 indicating there are 4 chlorine atoms per carbon tetrachloride. And we're going to look at formulas a little bit more, and then we're also going to look into naming, right? So this name here, this tetra, implies 4. And then ionic and covalent compounds are named differently depending on some rules that you are going to learn. But before we move on to naming, let's take a look at different kinds of representations for the same compound here. Okay, so molecular compounds can be represented as the molecular formula, and then it can have an empirical formula here, right? So there's the lowest ratio here. If you divide this by 4, you end up being CH2. So this is called the empirical formula. That's the closest ratio. The molecular formula indicates, well, we actually in one molecule we have 4 carbons and 8 hydrogens, and so there are actually several different ways you can combine 4 carbons and 8 hydrogens. And so sometimes you'll see a structural formula or even an actual structure, but it takes longer to do that, of course. So here you have a CH3 group that tells me that I have a carbon with 4 hydrogens. Then I have a CH group, and then I have another CH group, and then I have a CH3 group. Okay, and then you may not be able to grasp that just yet, but you can then, based on what you have, you can actually fill in the blanks and figure out filling up everything with 8 electrons. You know that's the structure. Let's just say if this is the structure, you don't have to want to draw this out all the time. You want to represent it as the structural formula. This helps me. This communicates connectivity to me. And then I can just represent that as the molecular formula or the empirical formula. All right, so, and you should be able to derive the empirical formula from the molecular formula, and this will come in handy. This will be used later on. So just for now, it's really just vocabulary, right? So understand that the empirical formula is the relative ratio of atoms here, right? So for C4H8, we are in a 1:2 ratio, which doesn't mean that you have 1 carbon and 2 hydrogens. It can mean you have 4 carbons and 8 hydrogens, or 2 carbons and 4 hydrogens. It's still the same ratio. So that's the empirical formula of C4H8 is CH2, right? You can divide both of them by a factor of 2. For B2H6, you can divide that by 2. You get BH3. That's the empirical formula of diborane. And for CCl4, you have no common factor, so CCl4 is the molecular as well as the empirical formula. So know the difference between molecular, which is the actual number, and if you do a chemical reaction, sometimes, let's say you do a combustion, you can determine the empirical formula, but not necessarily the molecular formula. So, but that we leave that for another day. Here are the 4 different representations for the same molecule. This is methane gas, which is part of natural gas. Natural gas are all of the hydrocarbons that are in the gaseous form, so we have 4 of them. Methane, this particular compound, is used for heating in not rural areas, so you use propane there, but most of the city gas here, if you live in town, if you're using gas for heating, it's the methane gas from natural gas. And it's called natural gas, but natural gas is actually all 4 gases together. Okay, enough. So this is the molecular formula CH4. This is what it actually, well, it's not what it actually looks like. It actually looks like this, the space filling model, right? Because it takes into consideration that this line, which represents 2 electrons, is an electron cloud. Okay, so here you have the black blob, which is carbon, and then these here the hydrogen somewhere in the center. So you have this. This is a good representation of, this is just almost a spherical blob of electron density, and you have different nuclei here. But for us, it's really clear. We can see it easier to draw a structural formula, right? And then the bond stick is a little bit more descriptive, I guess, but the space filling model is really what it looks like. And so there's a ton of these organic compounds or molecular compounds out there. And benzene, for example. And so look at the structural formula here, right? So you've got these carbon-carbon bonds, and there are alternating double bonds here. And I don't want to go into great detail, but if you sum it all up, you get C6H6. And of course, you can divide that by 6. So the empirical formula is just CH in this case, right? And so it's the same thing for acetylene, which is C2H2. It's also just CH. So the empirical formula for benzene and acetylene is the same, but the molecular formula, of course, and it's a completely different substance. I guess we don't really have to go into any great detail. I might want to point out that there is some reasoning behind how many bonds we have, how many electrons, and that it comes down to knowing the valence electrons, right? So if you have carbon with 4 valence electrons, you understand that carbon is in the second period. It has an s orbital and a p orbital, and if you fill that entire shell up, you need 8 electrons. So carbon needs 4 more electrons, and if it does that by sharing, it's going to have to make 4 bonds, right? So carbon is always going to have 4 bonds, right? So it can either make a bond with a hydrogen, like it does in methane, or like it does here, right? So with one of them, it does that. And that's fine. It can do that with all 4. Let me go, let me stay here. Or it can actually make another bond with another carbon. So this is how you get these infinite combinations of organic compounds here, right? So you just make these carbon-carbon bonds here, like in glucose. You got quite a few carbon-carbon bonds, right? And so you're just limited by the number of electrons here, right? So you just whatever you do, you can actually also make a double bond. You can take these 2 electrons and make a double bond, and then let's say you make another hydrogen, hydrogen, and hydrogen, and so well, I should have done that one more time. We would have had acetylene, but you get the idea. So everything here happens for a reason. And so what's not shown here for ammonia, for example, is, right, so well, ammonia should do that too, right, but it has 5, so it's not shown here as that there are 2 electrons. And so nitrogen, all of these carbon's going to make 4 bonds, nitrogen's going to make 3 bonds. Nitrogen has 5 electrons, so nitrogen needs 2 more. Okay, enough of that. Let's move on to naming. I'll just get started on it, and then maybe start the next lecture here in a second. So naming simple compounds, right? There's a lot, but we're just going to name very simple compounds, binary compounds, meaning things that have two atoms for the most part. And we call the naming, we call that nomenclature. That's what chemists call that, chemical nomenclature. And it's very systematic, and it just helps communicate the compound, and so you don't have to draw it out. You can give it a name. If I say sodium chloride, you understand, oh, okay, that's NaCl. Or if I say carbon tetrachloride, oh, that means there's a carbon and 4 chlorines here, and also understanding that you have a covalent versus ionic. So we have two different naming schemes. One is for ionic and one is for covalent, and you have to distinguish between them. Okay, and so we're going to practice just ionic compounds, and then we're going to practice just covalent compounds, right? And so you always have to distinguish them, right? And you should know by now the metal and a nonmetal and a nonmetal and nonmetal. Okay, what do we have here, right? So we're going to name ionic compounds first, right? So all we're looking at right now are metals and ionic compounds. So sodium, calcium, aluminum, and down here we have lead, okay? And so if they're by themselves, and if they're ionic, they've already lost their electrons, right? Sodium is in group 1. It's going to be +1. It's no longer going to be sodium. If I say sodium, I mean Na, the metal, with an electron. If I say sodium ion, I mean, oh, okay, I mean it's already ionic, okay? And so everything in group 1 is going to be +1. Lithium's +1, sodium's +1, because they have one valence electron, and when they turn into their ions, they're going to lose one electron, be +1. Calcium is in group 2, they're going to have +2. Both electrons are gone. Aluminum is in group 3, it has 3 valence electrons. It's going to lose 3 electrons and turn into aluminum ions, okay? And then we have some metals that can have different kinds of charges, okay? For example, lead. Lead can either be +4 or +2. All right, now let's go to the periodic table and take a look. Oh no, I want to go to the periodic table. Okay, we'll come back to why lead does that later. But the transition metals also will have different charges. You can have, the transition metals have the ability to lose different kinds of numbers of electrons, right? For example, iron can either lose 2 electrons or 3. So iron can be +2 or +3. And some things like chromium can be +6 and +5 and +4. They can have numerous oxidation states. Oxidation states are charges. Okay, so they can and the same thing is true for lead and other metals that are in the main group. Okay, so anything, some metals are always going to have the same, and some can have two different ones. Okay. If you can have different charges, you don't just call it the iron ion. You indicate the charge of the particular ion, right? So if iron can either be +2 or +3, what you do is you write that as a Roman numeral, right? So iron 2 ion means that it's +2. Iron 3 means it's +3. And copper can do the same thing. Copper 1 and copper 2. Zinc cannot. All right, zinc can only have one charge. Let's take a look at the periodic table to make things a little bit easier and explain what's happening here, right? So this is remember that these things over here, oops, yep, are nonmetals. So we don't worry about them at this point. Oh, I'm enjoying myself. This is kind of fun, actually. Yeah. All right. Okay, stop it. Yeah, okay, done. All right, so we said that everything in group 1 with one valence electron will be +1, as is indicated here. Everything in group 2 is going to be +2, and then I sort of lied and said everything in group 3 is going to be +3. Is not true. Okay, only aluminum is always going to be +3. What happens once you slip below the fourth or below the third period into the fourth period? What happens here, those d electrons, they have a shielding effect. All right. So we have those, let's just take a look at gallium here, right? So gallium is going to be 4s2, and I'm going to do 3d10, which of course is full, and then you have the 4p1. All right. So what happens is that these d electrons shield the s electrons. That means that it can lose either all of its p's, so one electron, so gallium can be +1, or all electrons, like aluminum does above. So gallium can be +3. And that same thing is true for indium. There's the same kind of shielding. So indium can be +1 or +3. Thallium can be +1 or +3. Okay, and that's due to the inert pair effect, which does not work for aluminum. Aluminum is always going to lose all 3 electrons. And so by the same logic, we see that for germanium, tin, and lead. Remember, lead was +2 or +4. Right, that's because lead is actually 6s2, and then you get those D's, which is the 5d10, and they are full, and they drop out, and then you have 6p2. So now you can either lose the 2p electrons, or you can lose all of the electrons, and that's how you get +4. If I go back 2 or 3, that's how you get +4 and +1. So what that means is that you have to communicate in your naming scheme the oxidation state or the charge if there are different charges. So anything here, any of the main group metals here, okay, polonium isn't going to do anything. So these here, except for aluminum, are all going to need a Roman numeral here, right? So like 1 or 3 for gallium, and gallium 1 and gallium 2. Okay, so gallium 1 is +1, gallium 3 is +3. And then we have these interesting phenomenons like zinc, right? Well, it makes sense that zinc would lose only the s electrons because it has a full d shell, right? So zinc is 4s2 and then 3d10, which means the 3d10 is full. It's untouchable. You're not going to remove it. So zinc is going to be only +2. And for the most part, that's true for cadmium and mercury too. And what also happens is, which is interesting, silver only has one oxidation state, right? If you remember, silver is one of those exceptions where the 1s electron is promoted to its d shell, right? Just so you got 5s2, this is what you expect, and then you have 4d9, but that's not its ground state electronic configuration. It's going to promote that one electron, so it's going to be 5s1 and then 4d10, and it's stable. It's not going to give up that electron. It will only give up this electron, so silver is always +1. You would expect the same thing for copper and gold, but it's not true. Copper can be +1 or +2. Okay, so if you do not see a charge on there, you have to communicate that with the Roman numeral. All right, let's take a little break here, and then there's a lot more to it. See you in a minute.